All right, class. So we're going to continue with solubility product. This is the last lecture on that. The last part is factors that affect solubility. There's 3 factors that would affect solubility, and that's common ion effect, pH, and complex ion. Now, because right now we're doing virtual online classes, I'm not going to focus on the last 2. I'm going to skip that, but if you want, you can read up on it. The one that I'm going to focus on, which we've done before a little bit, is a common ion effect. But I just want you to know that the pH and complex ion formation, they also affect solubility. Now, I'm not talking about KSP. I want you to be very clear with that. I'm talking about solubility. I'm not talking about solubility product, because solubility product, KSP, is a constant. And like any other equilibrium, the equation KSP, which is the equilibrium constant, is only dependent on temperature, right? Is temperature dependent and is only temperature dependent. But we're not talking about KSP. We're talking about factors that affect solubility. They affect X basically. But by solubility is molar solubility, the factors that affect X. So the one I'm going to focus about today is common ion effect, and we're going to do a couple practice problem with that. But just know that the pH and complex ion formation also affected, but we're not going to focus that for Chem 1B this semester. Okay, now let's do a practice problem. Okay, so here's our first problem. What is the concentration of lead 2 ions when PbI2 is dissolved in water? I'll give you the KSP. Pause me and then do this problem. Easy problem. Okay. Hopefully what you did after pausing me, you said lead 2 iodide is an insoluble solid. So I'm going to have an equilibrium because I know to some degree it would break up into ions. And then again, don't forget this would be a solid. This would be minus X. This would be X. This would be 2X. Then I'm going to write the KSP expression for that. Concentration of Pb plus 2 times the concentration of iodide. Again, you have to do it to the power of 2. Okay, now PbI2 is not part of it. Why is it not part of it? Because it's a solid. Now, my lead is X. Now, I2 is 2X to the power of 2. And the KSP is what? 6.5 times 10 to the minus 9. I mentioned this many times. So one more time. Again, the 2X would be the concentration. You still have to do it to the power of 2. And don't forget to make sure you get the math right. If you get the math right, it will end up being 4x cubed. What am I going to end up for x? What am I going to end up getting for x? For x, I'm going to end up getting, give me 1 second. Okay. For x, I'm going to end up getting 1.2 times 10 to the minus 3. That is my X, okay? That's my molar solubility, which will be the same thing as lead to ion solution because it's a 1-to-1 mole ratio, okay? So that is my X, which is also my lead plus 2 ions. Now, here's the next question. What is the concentration of Pb plus 2 ions when PbI2 is dissolved in a solution? That is 0.275 molar calcium iodide. Again, you should also be able to do this. So pause this and then give this a shot. Hopefully what you said the same as before. Of course, we have PbI2 solid. That hasn't changed, right? It goes back and forth to Pb plus 2 plus 2i minus. I always do this just because it makes it so much easier to see this. Now, the solution has also calcium iodide, okay? Now, calcium iodide is 100% soluble in water. It will break up into calcium and then 2i minus. Now, what type of problem do we have here? Hopefully, you shouting the answer saying this is a common ion problem. Calcium doesn't really do anything because it's not part of this equilibrium whatsoever, but I minus is part of the equilibrium, right? So here we have I, here we have I. So what type of problem do we have? Common ion effect, right? We have a common ion effect. All right. Now, what I have is I have 0.275 molar calcium iodide. But my common ion is iodide. So what do I have to do here? What I have to do here is I have to do a mole ratio, right? So for 1 mole of calcium iodide, I have 2 moles of the I. Do you guys agree? So it's a 1-to-2 ratio. So what I would end up getting is 0.550 molar of my I minus. Okay, again, because when this breaks up, I have one of these, but this has 2I, so I would have to times it by 2, because when this breaks up, this has 2I. You guys are following me so far? Okay, great job. Now, I can do an ice table if I want, or you can just conceptually do it. So at the beginning, of course, we have none of this, we have none of that, but at the very beginning, I do have 0.550 molar of I minus. Like before, right? We've done this before. This is my minus x, this is 2x. I'm not even gonna do anything with this because this is solid, does not make any effect on the equilibrium constant. This is x, this is 0.550 plus 2x, because it's a common ion effect. I already have some of this in the solution. So I'm going to go back to my KSP. KSP was concentration of lead plus 2 ion times concentration of I to the power of 2. That one has not changed. So my KSP was, I think I can find out if KSP from before was 6.5 from part A times 10 to the minus 9. This is x. Now what this is 0.550 plus 2x. I still have to square it, right? Because remember, again, this thing is just going to be my I concentration. It still has to be squared. So if I do this, again, don't forget, make sure you get the math right. And what I'm going to do, I'm going to assume this is 0, and I can assume this is 0 because 6.5 times 10 to the minus 9 is so much smaller than 0.550. So I can definitely assume it's 0. Whatever this number is going to be so tiny compared to this. So that makes my math a little bit, more than a little bit, a lot nicer. That would be x times 0.550. Don't forget to square it. That should still be going on. So if I do this, what I end up for x, I'm going to end up with 2.1 times 10 to the minus 8. Now, does this make sense? My molar solubility, which is the same as lead plus 2 ion. Did you expect it to go down? We did expect it to go down. We've talked about this before. We expect it to go down. Why did we expect it to go down? Because this is an equilibrium, right? This is an equilibrium. Now, if I have one of the common ion, that means I have one of these, then the equilibrium is going to shift to the left. So if I have one of the common ion, the equilibrium is going to shift to the left. I have this, it's going to shift to the left to reach the balance again. So if it shifts to the left side, then I'm going to have more of the solid and less of the ions. So less will dissolve. And this is exactly what I expected. So what does that mean with common ion effect? What would it do? Common ion effect, what's going to happen to the solubility? Solubility would decrease, right? Solubility would decrease. So solubility will go down for the common ion effect. Again, why would it go down? I'm just going to, let's just put mx going to m plus a. If I have one of the common ion, doesn't matter which one I have, what would happen is the equilibrium will shift this way, right? The equilibrium will shift this way to reach the balance. Le Chatelier principle. One of these go down, it will shift the other way. So I have more of the solid and less of the ions. Okay, now so far so good. Nice job. Let's do one more practice problem. Okay, here's our next problem. Now, here's again the same thing as before, but before I write down the equilibrium equation, what I want to point out here, they give you the pH, right? They give you the pH. So I have to do something with this pH that is given to me. Okay. Now here, if I write the equilibrium equation, I have nickel hydroxide, again goes back and forth. It would break up into nickel ions plus 2 OH minus. Okay. Nothing we haven't seen before. You guys agree? Now, this is not dissolved in water. This is dissolved in a solution that has a pH of this. Now, every time I have a pH, what could I figure out? I could figure out H plus concentration, which H plus concentration is not going to do me any good. But what would do me good? The OH concentration. Well, I know how to do that, because if I go 14 minus 10.72, I get 3.28, and that would be the POH. Now we're getting somewhere. Because POH is equal minus log of OH minus, right? Okay, so now I'm getting somewhere. So my OH concentration would be, again, make sure you get the math right here. It would be 10 to, make sure you get the math right here, it would be 10 to the minus 3.28. I have to take the anti-log of it, right? I have to take the anti-log of it. Okay, so if I do that, what I end up getting for that, I end up getting 5.2 times 10 to the minus 4. So I got an OH concentration. So this is not dissolved just in water. It's dissolved in a solution that already has some OH minus in it. Now, what kind of solution, what kind of problem is this? What do you think? Yeah, this is a common ion problem. At the beginning, I have none of this, but at the beginning, I have some of the OH minus. Is a common ion problem again, right? Because I have some of the OH already in the solution. Okay, so now, again, I did this before. Again, you don't have to do an ice table. If you want, you can do it. I'm doing it both way in this practice problem. So last one I did an ice problem. I can do this one, not to do one, so you get used to both way of doing things. So I have a KSP, right? KSP is 2.0 times 10 to the minus 15. Again, this is exactly like before. You agree? Now remember before. Again, this is minus x, this is x, and this is 2x. That has not changed. So nickel is x. Now hydroxide concentration is 5.2 times 10 to the minus 4 plus 2x, and then to the power of 2. Again, this is exactly like before. It's a common ion problem. I have some of this at the beginning in the solution. I have some of this from the beginning in the solution. The last problem I did an ice table and I did all that. I kind of skipped that. You could do it, you could not do it. Hopefully you get to the point that you're going to be able to do this very quickly. All right. So again, can I assume this is 0? Yes, I can definitely assume this is 0 because the KSP is so tiny compared to this value. So whatever this is, it will be very tiny compared to this. So if I do this, what my x is going to be, and again, don't forget that when you do this, don't forget, let me actually do the math because I want to make sure everyone's on the same page. So I have a KSP is 2.0 times 10 to the minus 15. This is x. So that's going to be 0, but don't forget 5.2 times 10 to the minus 4 has to be squared, right? Don't forget that. So what I end up getting for, oops, I did not just do that. Okay, so what I end up getting for x, I end up getting 7.4 times 10 to the minus 9, which is a molar solubility of nickel hydroxide. Okay. Now, I want to make a couple of side notes. Side note 1, don't forget that KSP is a constant. Common ion effect is not going to affect KSP. Ksp is a constant. It does not change by common ion effect or other factors. Molar solubility, which is X, does. Molar solubility does change with common ion effect and other factors, but Ksp is a constant. The only thing Ksp is dependent on is temperature. So Ksp, solubility product constant, is only temperature dependent. Molar solubility, that is affected by common ion effect and other factors. Okay. All right. Nice job. I will talk to you guys next time.